Good afternoon. My name is Shreya, and I'm a technical product manager, and I'm joined by Keshav, who's a software engineer. We both work with Expedia, and we're here to talk to you about how you too can find the needle from a haystack. What is the needle we're talking about, and what is the haystack? Let's talk about it slowly as we go. So I'll start by answering a couple of basic questions like the who, the what, the why, the where, the whens. And Keshav is then going to take on, and he's going to talk in depth, in a little more detail about what the product is, what this solution is, and how you can also use it. So who are we? So we are both engineers who work for the Expedia group. Maybe you guys have heard about Expedia. It's an online travel agency. And the mission is to bring the world within reach. And we as engineers use technology to kind of help the company fulfill this motto of its. The what? So what is this solution that we're talking about? If I have to tell you about it in just two simple words, it's a diagnostics tool. So a little bit detail about it. Haystack is Expedia's first open source tool, which was made since day one in open source. We wrote the first line of code till the very end. We've been in open source. It's a first for the company. So we're really happy to be speaking about it in the open source community track. And what it basically does, it takes the information of your system and kind of helps you diagnose issues. Maybe we're coming a little closer to what is the needle and what is the haystack. So the why. So why do we need this solution? Why do we need to find some needle, this small thing in the sea of something, the haystack? So for that, I have to take you through the journey. Like 1960s, we started with the mainframes, all the way till the microservice architecture. In the 2010, we're in its era. It has lots of pros. It helps you take this monolithic architecture, break it, slice it, dice it into logical entities, tons of microservices, which then interact with each other and then do the same purpose of what the monolithic used to do. It makes it much easier, much logical for you to work on these things, but it also comes at a price. And to help you understand that how in Expedia or in any other company, when the consumer comes on the browser and starts to do a transaction, it comes right from the browser and then goes all the way through the architecture. It can go through cloud, non-cloud, data center, one service, 100 microservices, multiple databases, and then it forms this response and then sends it back to the consumer. So yeah, like I was saying, the con of microservices. You can clearly see from the face of this developer, she's not happy. And why is she not happy? Because she's not able to find, again, that needle in this haystack. So without further ado, let us tell you what the needle in the haystack is. The needle is the root cause. It's the issue. It's the pinpoint. It's that one service or the point of failure, which is happening in your microservice architecture. The microservice architecture is a bunch of microservices. Could be 5. Expedia has about 20 to 100 microservices. So that is the haystack, and all these developers, everyone is just trying to figure out that one needle where things went wrong. So this solution helps you diagnose that. So a little closer to understanding the needle in the haystack. So how are we doing this? What is this solution? Did Expedia come up with it? No. The solution was always around. The solution was something that Google actually published, a paper called Dapper. And in Dapper, Google talks about and introduces the very basic building block of this tracing tool, which is distributed tracing. What it uses is basically your transaction logs. But how it does that is something that you can understand simply here. So when the consumer comes in and it sends a request, goes to one service, then second service, then third service, and then kind of comes back with a response. That's how it usually works, right? Simplified way. What distributed tracing does is that it tells you to add certain extra fields which then will help you diagnose the issue faster and more easily. So what are those three? So the first one is the trace ID, as you can see here. The trace ID or the transaction ID or the activity ID, any name you can call it, but what it is a logical entity of a consumer coming and doing some action on your website and then getting the response. That is one transaction. And you have identified that as one ID called T1. So all service 1, service 2, service 3, all three of them have one transaction ID, which is T1. And that's how you identify them as a whole. Now, okay, so now you know that if there is some issue happening, you can pinpoint exactly which transaction. Is it T1? Is it T2? Is it Tn? Which transaction it is in. But to further go down into which service within this transaction is the issue, you need another ID called span ID or the message ID, the M1s that you can see here. So every unique service in this would have a unique ID number, which is the M1 for service 1, M2 for service 2, M3 for service 3, and so on. So now what do you have? You have this bundle of microservices, and out of them, the whole bundle is identified as T1 or transaction 1. And within that, all these services, they're all identified as service 1, service 2, service 3, service 4, all with a unique ID. So now you can diagnose two things: which transaction the issue was in, and then in which service, because you can now uniquely identify all of them. What is the third one? The third and the most important ID is the parent message ID. So now you know the whole bundle, you know them uniquely, and you now also know who is calling whom. Who is the parent of service 2 here, service 1? Who is the parent of service 3? It's service 2 now, and then so on. And service 1 does not have a parent. So what is service 1 then? It's the first service in this whole transaction, in this T1. Why? Because it does not have a parent. So that's how you identify these things. This is the basics of distributed tracing diagnostics, on which actually multiple tools are made. So this is like a waterfall. So think of all these as a waterfall. It's a cascading waterfall. So the entire thing is one T1. All these individual cascades are a different service, but who comes after whom is determined by the third parent message ID. So just a visual mapping of what we just spoke of. So yeah, so how many companies already have such implementations who needed diagnostics? They were suffering. They were not able to identify issues in time, a lot of losses, and sometimes you still couldn't even after a long period of time, and bugs would continue. So Twitter actually came up with the first implementation called Zipkin in 2014. And then from there onwards, Uber made Jaeger. Similarly, at that time, Haystack came up with Expedia came up with Haystack, and then AWS was coming up with X-Ray, Amazon AWS. So basically all these implementations, different implementations, concept is same, distributed tracing, which we just spoke about. So why Expedia needed to build its own system? Why couldn't we just take Zipkin or Jaeger or any other tools? So Expedia started in 2015. By then, there was just one tool called Zipkin. And these were the things which we didn't find at that time in any of the tools, and hence we decided we needed our own implementation. First one is the UUID support. It didn't have that, and Expedia all works on UUIDs. Second most important one, we wanted to make the system in a way that you can use the same data for many other things. The third is open tracing. So if every organization here is using open tracing, what is the compliance? So open tracing compliance is the standardization, basically, of distributed tracing. And then open source. So it gave Expedia an opportunity to come here, share these tools with everyone, and encourage them to use it. The next slide, like I had promised, we're going to go into a little bit of detail about how we did it, how we've architectured it. And for that, I'm going to invite Keshav on stage.
Thanks, Shreya. Hi, everyone. As Shreya mentioned in the last slide, that we needed an extensible platform. We have so much data coming into the tracing system, and we just don't want to do the tracing. So we came up with a design of a decentralized system with Kafka acting as our central nervous system. So the ideology of the entire Haystack architecture, as you can see, is based on 3 principles. We needed a system which was componentized. That means all subsystems within this system, they should be ready to be used, and anyone can replace any subsystem or extend any subsystem to better suit their needs. So we needed the componentization of that system. We needed the system to be resilient. There should not be a single point of failure for that system. If any subsystem goes down, it should not impact the other subsystems. And we needed the system to be scalable. We needed it to ingest the entire traffic of this of the org, like the Expedia org or any other org who wants to onboard to the Haystack. So we needed each subsystems to individually scale and not depend on any other subsystems. So that was the reason we came up with a decentralization of the entire Haystack architecture. Now, as you can see in the picture behind me, that we have the entire Haystack architecture. It's divided into 3 pieces. One is the subsystems, which are traces, trending systems, service graph, and I'll talk about these subsystems in a bit. And we have data stores. We support 3 data stores out of the box, which is the Cassandra, which is used to store the traces. We have the Elasticsearch, which stores the indexable fields. We have metric tank, which is backed by Cassandra, to store trends in a metrics 2.0 format. So, and then we have the visualization. So we have a UI called the Haystack UI, which actually shows us the entire processed data from each of these subsystems in a single place. Maybe the trends, traces, the service graph, the latency graph, and other things. So I'll talk about the subsystems, what we have out of the box, and so we have 6 subsystems out of the box, which is the traces, the trends, the service graph, the latency costing, the alerts, and the pipes. And I'll talk about each of these subsystems as to how what the architecture looks like in a very minute, at a very uber level, and I'll talk about how these subsystems they look, how you can visualize them in the UI, and how you can diagnose or find that needle in that haystack. So let's talk about the traces, which is the most important subsystem that we have. The traces subsystem, it's the subsystem that does the distributed tracing and helps us in diagnosing that the problem in that microservice architecture. And it has 2 components, which is the indexer and the reader. The indexer does nothing. It just groups the spans that we are getting from individual services into a single unique trace and sends it into the Cassandra. And we have Elasticsearch, wherein we send the indexable fields. Then we have the reader. It just helps our UI, and it fetches the trends, the traces from the Cassandra, and all the contextual searches are powered by Elasticsearch. So the reader helps the UI, and let's see how the UI looks like for the traces component. So as you can see, we have the main page of the traces component. We have the first, it's little blurred, but I'll explain. We have the first, the header kind of a thing is the search bar, which we say a universal search bar. You just specify what all the indexable fields that you have in that particular search bar, and then you have the timeline view. This timeline view actually helps you drill down to the traces in a particular time bucket window. You can click to any of the bars in this timeline view and you'll drill down to that particular trace in that particular timeline window. And then you have the traces view, which is just the list of traces in a tabular format. So let's say if someone clicks on a particular trace, what happens? As you can see, you have the waterfall view of all the downstream services. So let's say we'll take an example. We had an external client that's calling one of our services, let's say the Stark service, and this Stark service is our end, like the first point when someone hits to our org, and this Stark service then calls the Westeros service, which calls the Tyrell service. So you have like there is a call from service 1 to service 2 to service 3. So you can see there is a parent-child relationship between these services in a dotted format, like the parent-child is being depicted in the dotted format. Now each horizontal line tells us what all services, or what each service is, how much time each service is taking. So we have, let's say, the Westeros service is taking 1500 milliseconds to complete the entire call, like its duration is 1500 milliseconds. And now you know, let's say this trace call failed out, you know that okay, it could be the Westeros service which is the root cause, and you can go and fix that Westeros service. You don't need to dig down as to and find out which among all the thousands of services that you would have, microservices, which one is causing the issue. So this is the trace waterfall view, and you can get all the logs, like the logs that you send to some of your to any of your logging engine, maybe the Elasticsearch to Index. You can send it as key value pairs to us, and you can actually look at those logs as well. We then come to the trench component. The trench component, it helps us in creating the trench for a particular service and operations, and we have two subcomponents in it, which is the transformer and the aggregator. The transformer does nothing, it just converts the spans that we are reading into a matrix 2.0 metric points, and the aggregator is the main component that actually reads those metric points, aggregates them, and processes them back into the Kafka in a metric tank format, which is, and this metric tank format can be consumed directly by the metric tank. And metric tank is a time series database. It helps us in keeping the time series data. And currently, out of the box, we support failure counts, success counts, duration, mean, median, deviation, standard deviation, 95th, 99th percentiles. All of these things that you see in Grafana and Graphite, they can actually come and see it over here. And we have the intervals. We have 1 minute, we have 5 minutes, we have 15 minutes, and we have 1 hour intervals. So we have everything that comes. So since we have all the data, we can always do the stitching and extend it out. That was the intention. So we have trench with us, and let's see how trench look like in the UI. So we have, when someone selects the trench tab, you can see, and someone says we have the root service, you can see the trench for each of the operations for that particular trending service. So let's say we have the count duration, we have the success duration, we have success duration, we have failure counts, and someone can click on each of these operations and get the detailed trend view. Like you can select, you can do a time range selection, and you can do a detailed view. So this is about the trending, and let's see what service graph gives us. So service graphs, when someone lands on Haystack page, home page, the service graph, it has it's a service mesh. It gives an overview of all the services that are integrated in Haystack and how they are interacting with each other. And like you have service A talking to service B and not to service C, you will get everything in a graph. And you can see the traffic information, like say how much is the request rate between the service A to service B, or how much is the error rate. So everything is given in the service graph at an overview. So someone who comes into the Haystack, you can get, okay, these two services are causing problems for me right now. So we have the latency cost. So I know, like every one of us who are in the microservice architecture, we have like cross data center calls, we have everything, and we need to know how much is the network latency in each of these when we are making cross data center calls and all. So latency component helps us doing that. We know like whenever we have a trace call, what all how much time is spent in network. So we have nodes that are there, that are services, and we have edges, and that tell us how much time is spent in the network. So it helps us in saying that, okay, let's keep service A and move out to the same region, or should we keep the service A in some other different region. So network latency component helps us in doing that. The alerts. Now we have thousands of services, thousands of microservices, and you don't want to come and see to each and every services. You need some alerting mechanism to help you do that. We have the alerting mechanism. So from the trends that we created, we can have the alerts for any anomalous trends or anomalous behavior of a microservice, and it can alert you out as to which operation is causing that particular anomalous behavior. And currently these alerts, they are powered by our internal system, which is the Doppler. but we have an adaptive alerting system coming up in the open source, which will help you in doing this, which will help you in powering these alerts. And these alerts, I'll talk about the adaptive alerting system in a bit. So yeah, the pipes. The pipes came up as a use case that we need to send the data that we have collected to some other external source, maybe the S3, or maybe to some external HTTP endpoint, or to a Kafka, an external Kafka. So, and the use case that we started with was to send data to S3 to do machine learning. With so much data that we are collecting, we can do machine learning, and maybe we can query the historic data. So we created pipes as a way to sync the Haystack data to any external source. And the way we do it with S3 is to send it via the AWS Firehose, or we send it to any external Kafka or to an HTTP endpoint. Now, how to onboard or integrate with Haystack? It should be seamless. The process should be seamless. So what we have various open tracing compliant client libraries, and just integrate with that client library and have a Haystack agent running in your box. So Haystack agent is a local agent that runs with your app. The client library sends the spans to the Haystack agent, which sends the traces or the spans to the correct dispatcher, or to the correct dispatch mode, which we currently have Kafka and the Kinesis as our dispatch modes, but we are always welcoming the contributions back. So yeah, the agent and the client libraries will make the integration seamless with your applications. So next steps, we have adaptive alerting coming up. It's anomaly detection and the alert generation OSS project by Expedia, and it's still work in progress. We have the repos in in the GitHub, and we currently will have many algorithms for anomaly detection out of the box, like static threshold, so that you can have Syrian out of the box. You will have cumulative sums, and you'll have all the new machine learning and the neural networks based algorithm coming up in this. So adaptive alerting is the next effort. And how we use Haystack in Expedia group.
Yeah, so Expedia group, technically it's not one group, it's a bunch of travel companies which are under the hood of groups. So multiple brands are actually using Haystack right now. We've also been speaking to a lot of other companies like British Airways, Salesforce, a lot of those ones to kind of come and start using this open source tool. And within Expedia, like I said, we have 2,200 microservices, and about 200 of them are already on the tool. So
yeah, so we ingest data at 210,000 spans, 210,000 spans per second. Mm-hmm. We have a 65 node Kubernetes cluster, and it's increasing. And we have a 40 node Kafka cluster. We have 50 node Cassandra cluster to store the data. We have tens of nodes of Elasticsearch cluster, and we have integrations with various open tracing compliant libraries like Java, Node.js, Go, and Python is coming soon.
And we recently started supporting integration with Istio. So anything new that's coming up in the world of monitoring diagnostics, we have a dedicated team that kind of keeps adding these things up. Next is that these are all a bunch of open source libraries. So we want to end this talk by sharing this with you guys, that we're really excited to be speaking in this open source community track, because I think our main mission out of this is to share what Expedia did, and also to help you use the same diagnostics tool, or basically the basics of how you do diagnostics, and invite and welcome all of you to come contribute here. And now we're open to questions.
Hi, I'm Raghu. And when you say open source, is it completely free for enterprises to use?
Yes. So basically, it's just kept in the open source as a repository. All you need to do is just fork it out and
clone it out and use it out.
Yeah.
Okay. So what is the alerting time? For example, how fast it can alert when there is a key performance indication?
So for adaptive alerting, the new adaptive alerting that we are coming up with, you can set the which level of alerting you want. You want alerting on 1 minute, you want alerting at 5 minutes, you want alerting at 15 minutes, or you want alerting at 1 hour. Okay. So it totally depends on you. It's all configurable. Mm-hmm. It'll depend. You'll have a UI that you can say, okay, I need alerting on this particular metric at this particular interval. let's say 1 minute. So after 1 minute, if it sees an anomalous behavior, it will do the alerting. We're doing a POC in our Expedia and we do it at 5 minutes and it works fine.
But a lot of our customers use a tool called Instana, but it can alert you within 3 seconds if there is an issue.
Which tool?
Instana.
I'm sorry, I've not heard of the tool, but currently, see, the way we work is we have the trending, and the trending works at 1 minute interval. So to do the alerting at 3 seconds, so there are two components to the alerting. Once is that you should have the data in 3 seconds, like every point that you are getting in the trending should be after 3 seconds. Again, that is configurable. You use your own trending, you update the configuration intervals, say you need the data after every 3 seconds, and you can then say the adaptive alerting system to configure it, like generate the alerts for the 3 seconds. So again, it's configurable. You have two subsystems. Adaptive alerting is not a subsystem; it's a separate system. But once you integrate both of these systems, you say the trending part, okay, I need the trends to be generated after every 3 seconds, and then that trends they flow to the adaptive alerting, and then you say to the adaptive alerting, okay, give me alerts on these 3 seconds trends, and it works.
So was there a question in that does it in 3 seconds? Anything you want to?
You said you'll keep all the traces, you will track all the traces on the applications, right?
Yeah.
So do you from end to end, do you trace, like every trace you keep a store of?
Yeah, we don't do any sampling.
Okay.
It's all, we keep it for 3 days, for 4 days,
Okay.
and then the historic data is pushed out to the S3.
Yeah.
Okay, so
And there also you can use the data for 30 days, so it's usable for 30.
So what is your data granularity?
Pardon?
Data
The
granularity.
data granularity.
We store the entire data. We don't do any sampling. So whatever the clients they send us, see I told you we have tags, like we have key value pairs, wherein the client sends us, let's say if a service is making an error, they send us the exception in that key value pairs. So we keep that data.
Okay.
So I'm not sure what you mean by the granularity.
Data granularity means Instana, what it does is it constantly grabs the data from the application and keeps on showing you the traces. So after 1 week also you can come back to your traces and understand how the latency is, how the error rate is.
Yeah, you can do that in this as well.
You can do it.
So I was interested to know how fast it collects the data from the application. For example, let's say I'm running an Apache application. So how fast it collects the data from the application?
So the latency is in milliseconds.
Okay.
So if you are talking about the latency, that how much from the time the trace was sent from your app and the time you see it in the Haystack UI, it's the latency is within milliseconds, but we show it after the seconds since the entire trace. So let's say you have tens of services that are interacting for a single request response. So you would have the traces coming up from each of these services. So to show the waterfall view, you need that 10 seconds because the entire request is taking 10 seconds to be served. So you need the entire traces to come out to the Haystack, and then we can stitch them together and show you.
And we would definitely encourage you to clone it and definitely see how you can configure it. Most of the questions you asked, definitely configuration based, and we do allow for that. And if you don't find something working, just contribute to it.
Okay, great.
Yeah.
So
Hi, Devidas here. Initial part of slide you mentioned you had a problem about open compliance, as in in later part of also I didn't see it addressed. So is it addressed yet, or if it is, how
we are
it
open
is?
tracing compliant.
Yeah, we actually didn't mention it as an issue. We mentioned that the few tools which were existing in the market, they weren't OT compliant. So when we made our system, we kept that in mind, that we want to make sure that we've standardized it.
Okay.
How much of overhead will it create with respect to processing power as well as data storage?
That's a great question.
With respect to the processing power, I'm assuming that you are saying when you are running the agent in the app.
Yes.
Yeah, so currently we have agents in like hundreds of services within Expedia, and the agent runs in the processing power of using 502 MB of RAM and around 64 millicores of CPU. So it's like very, very minimalistic.
Quite
processing.
negligible.
Yeah,
Right.
it's almost negligible.
Yeah.
So we have optimized agent to run in the minimalistic ways.
And also we have some stress numbers there, like even if you have this humongous amount of data, we still have done quite a bit of stress testing. So you can match those numbers there as well.
Thank you.